You know, the world's been pretty chaotic lately, but I just wanted to bring a little more chaos to your plate.
You see, I'm not talking about this or this, and as much as we love Tom Holland, I'm not talking about this either.
You see, I'm talking about chaos theory, and let's just see what our good friend Google has to say about that. Oh wow, look at that! Chaos theory is a branch of mathematics that deals with complex systems whose behavior is highly sensitive to slight changes in conditions so that small alterations can give rise to strikingly great consequences.
Hold up, what? Okay, so before we dive into that mess, let's take a couple steps back and start at the very beginning.
Let's start at the very beginning.
No. We're not singing this. Okay, back to the beginning. So this cool dude here is named Edward Lorenz. He basically started the world's interest in chaos theory back in 1961. He was trying to predict the weather by modeling weather patterns on his computer. Computer? Okay, we'll call it a computer. Anyways, he discovered that when he ran the exact same simulation but with a small difference in the rounding, he got completely different results. This was completely unexpected. However, this is the root of chaos theory. You see, Lorenz discovered that the huge difference in modeling results occurred not because of any errors in his computing, but because weather is a chaotic system, which means that small changes in the weather early on can have huge effects later on. This is known as the butterfly effect. The name stemming from the joke that a butterfly flapping its wings in Brazil could cause a tornado all the way in Texas. Who knew butterflies could be so dangerous? Now let's get back to the definition of chaos theory, but don't worry, I'll break it down for you. You see, chaotic systems have three main properties. 1, 2, 3, easy as that. Number 1, chaotic systems look random. This means no periodic motion, but the behavior of the system depends on the previous behaviors and conditions of the system. For example, flipping a coin looks random, but it is not chaotic because each flip does not depend on the previous flips. Number 2, they are non-linear. This basically just means that they cannot be modeled by a straight line. Number 3, chaotic systems are sensitive to initial conditions, like we just saw before with the butterfly effect. Okay, so now I'm going to show you a little at-home demonstration of chaos.
So here I have 2 recordings of a double pendulum. Although there are only Newton's simple laws of motion and action, it's still a chaotic system. Let's check out those 3 properties. Number 1, you can't predict what will happen by just looking at the pendulum, but still each swing depends on the swings before it. Number 2, if we were to model this pendulum, it would be non-linear. Number 3, the double pendulum is sensitive to initial conditions. We see that the 2 pendulums start in sync, but become out of sync by the end. This is because the tiniest change in where we start the pendulum changes future motion entirely.
And there you have it. There are the 3 properties of chaotic systems.
Well, that's a wrap on chaos theory. Thanks for watching, and remember, beware of those butterflies.